All right, we want to look at how heat moves. And so on a molecular level, we can look at the molecules colliding off of each other and transferring momentum. So we can look at a momentum transfer. That causes a transfer of energy in the collisions. And so we can look at a collection of collisions coming about. And so this would happen if the molecules are in contact. And so when substances are in physical contact, we call that form of heat transfer conduction. Now what it looks like is the model that tends to get used is we think of an object and a secondary object. At two different temperatures. And what will happen is we'll connect them with some physical object. So think of the inside of an oven and the room and the glass that separates them. And so we'll put the glass in the yellow box there. And what will happen is the heat will flow from hotter to colder. And so we'll say this is at temperature 1, and this is at temperature 2. And temperature 1 is going to be greater than temperature 2. So T1 is greater than temperature 2. My pen just went nuts on me again. Sorry about this. My office setup in the school seems to not like the tablet as well. And so let's talk about how we're going to model this. So what we're going to do is we're going to put some cross-sectional area that the heat's flowing through. So in this case, I guess the imagination we're going to use to build the mathematics, so we can think of a block of something at one temperature and a block of something at another temperature, and it's connected by a rod. And the rod has a cross-sectional area. And there's some length between them. And so we have the greater temperature to the colder temperature. We have some substance in the middle that has a cross-sectional area, has some depth to it, and we have a length. And so what's going to matter for us is the ability of this substance in the middle to transfer heat. And we measure that with a constant called K. And so K defines how this substance allows heat to flow. And so there's some things we'll take from this. First, heat flows from hot to cold, always. It will flow until the two substances are of equal temperature. And the nature of the material determines how quickly heat flows. And so what we'll do is we'll make how quickly heat flows. The amount of heat per time is equal to that K constant times the cross-sectional area. So how thick this is will determine, plus the K constant. Then we need the greater amount minus the lesser amount divided by the length. And this will push heat through. And this is how quickly the heat will move through. A couple of things to note. The difference in temperature drives this. As these get closer and closer in temperature, the rate of the heat flow goes down. Now remember, this is a whole bunch of particles hitting each other, and there's a lot of randomness to it. And so they're going back and forth and back and forth. Some energy from here is lost to here. And some energy from here is lost to here. Because this has more average energy, it's losing more than it's gaining. But as they get closer and closer, that difference gets smaller and smaller, and so this happens more slowly. So when we look at heat flowing, it flows from hotter to colder, and the rate is driven by the difference in temperature. Then in what we put in the middle acts as a damper to that. So we could think of this as this would be a high mountain peak and this would be a lower peak, and the water flows down. And if we put something in the middle, rocks or different types of dams or things in the middle, it will slow the rate of flow, if we want an analogy. But the key is the difference in temperature is the driving mechanism for the rate of change. What we put in the middle slows or lets that impedes that. So let's look at an example we can do here. Let's say we have a glass window, a modern glass window. And so we have the glass window, and then in the middle of it, we have an air gap. So let's see if I can get my air gap drawn here. And then that touches another window on the outside. So we kind of have these stacked windows with an air gap in the middle, right? You look at your window at home, and it has this dead air in the middle to hopefully help slow it down. And what I'm going to do is, well, that's the modern window, and that dead air gap slows it down. Let's just look at a single pane of glass, and then we'll put the dead air in the middle. So if I have one pane of glass, on the outside I have the outside temperature. So let's say, what is it today? It's it was 12 degrees Fahrenheit. I'll say negative 4 degrees Celsius. And then on the inside, well, we're going to keep it at scientific room temperature, about 22 degrees Celsius. And so this piece of glass controls the rate of heat. So we have to burn fuel to keep it at 22 degrees. This temperature is going to want to drop. And it's going to drop at a rate. So let's find the rate this drops, or how many joules we're losing per unit time. Now, think of it this way. If I want to keep the room 22 degrees Celsius, I have to replace the energy at the same rate. So I have to burn fuel equal to that. So if we just have a single pane of glass, then we look at these. So going into the book, let me get here. So my Q per unit time, how much heat I need to keep replacing, and my K constant for glass is 0.84 joules. 0.84 joules. So 0.84 joules, let me get the unit on this right. The K constant, oops, the screen shifted over here. Shift back, there we go. 0.84 joules per second meter Celsius. Oh, these K constants have weird units. Joules per second meter Celsius degree. And then in the cross-sectional area of the window. So what is my window here? I've got, if I measure it, my window is, well, it's roughly a meter by a meter. So we'll say 1 meter squared. I have a slightly bigger window than that, but think of a yardstick squared. Will be a good estimate. And so then we have 22 degrees Celsius minus 4 degrees Celsius. And then the length is the thickness of a window, and a standard window is about 1 centimeter thick, which is equal to 0.01 meters. All right, so we're doing an order of magnitude estimate on how much joules we're losing per unit time. So 0.84 times 22 minus 4 divided by 0.01. I get 2,181 joules per second. Is going to bleed out through the glass. And so one of the things we do to slow that down is we add an air pocket. Now if we take the same calculation and we make an air pocket, then we're just going to look at the air pocket, how much is transferring through the air pocket, and how this will slow it down. Air has a thermal conductivity of 0.023. So if we rerun this calculation with 0.023, and we're not worrying about the pane of glass on either side, we're just letting the air pocket on either side of the glass go through, or how much the air will slow it down. So 0.023 times 1 times 22 minus 4 divided by 0.01. Type that in right. That's 59.8 joules per second. And so one of the biggest things you can do to slow down heat loss is create the double pane windows that we see. 2 panes of glass with dead air in between them, because the air transfers heat more slowly. And if we mentally think about what we're saying conduction is, it's the particles touching each other. Well, air has less particles in it than a pane of glass, and so you slow down the heat transfer. And so the heat in here will heat up this piece of glass. This will heat up the air, but it will happen slowly. And so when it's transferring heat out to the cold, this air pocket slows it down. And so conduction has to deal with the molecules touching each other. There's another form called convection. Now, convection happens when a fluid changes density. So if we have a fluid, like water, and I'm heating it from below, and this heat will cause the water immediately underneath it to heat up. Well, this will cause it, once it's over the 4 degrees Celsius limit, to start getting less dense. And as it gets less dense, Archimedes' principle means a blob of water here will start to float. So as it heats above the 4 degrees Celsius limit that we talked about before, right, that the 4 degrees to -1, water gets less dense as it starts to freeze, which causes it to expand. But after we get above 4 degrees, it will expand again as it heats up, and it will move. And as it moves up, it brings all of its heat energy with it. That causes a space for colder water to come down. And what happens in convection is we get these things called convection currents, which generally, if you have a substance, it'll start rising in one place and coming down in the gaps that fill it. And it'll make circular systems. And as it rises, it might lose its heat to the cooler surroundings up here and gaining heat from below. And so it causes this circular motion. This is what we see with winds coming through. We have places where the land mass is heat, causing the air to rise, which causes colder air to fall in and fill the gap. And so the Archimedes principle that we learned within fluids applies with us changing temperature, and it causes convection. And so convection is the transfer of heat by fluid motion. Now notice, in the end, convection is an augmented form of conduction. These substances will gain and lose heat based off of conduction, and that will cause them to physically flow. And when they physically flow, they transfer heat again based off of conduction. And so we have conduction, we have convection, which is a fluid flow caused by the change in density. And then we're going to have one last form called radiation. Now radiation is really interesting. We will learn a little bit later charged particles, which is all matter, positive and negative. Right? You have protons that are positive inside an atom, and you have electrons, which are negative inside an atom, and they're charged particles. Now, one of the things charged particles do is inside of space-time, they drag on space-time. And Maxwell realized this is what causes light. So we can think about a charged particle, right? Some proton and some electron in an atom, and their motion, the motion of a charged particle, leads to the generation of light. And light is the transfer of energy away, or we call it radiation. And so a charged particle vibrating, a vibrating charged particle, emits electromagnetic radiation. And that's in the form of a photon, which is a packet of energy. And so the vibration of any matter causes this charge to kind of drag through the emptiness of space-time, and it will cause it to vibrate, and that'll emit a photon. And we're going to learn about this in a little more detail. But for us, that means that anything in motion loses heat through radiation. And one of the common ways we see this is called is infrared. Your body is at a temperature, so all the molecules in your body are vibrating up and down, and so they are losing energy as these plus and minus charges have to move up and down due to the particle motion of everything. That causes those particles to have a reaction with space-time that releases photons. And those photons happen to be mostly in the infrared spectrum, and so we see them as infrared. In fact, the temperature that an object is vibrating at determines the peak wavelength. And so what we can find is Stefan Boltzmann and Planck and Wien worked on radiation laws to figure out how much radiation was being emitted by light. And so the transfer of heat due to electromagnetic radiation is, oops, that's an equal, is equal an epsilon, which is an emissivity constant. It's this number E the epsilon emissivity constant is between 0 and 1. If it's 0, you don't emit any radiation, and if it's 1, you emit nothing but radiation. And generally we see this as if it's black versus white, how much radiation is being emitted. And then sigma, which in this case is the Stefan Boltzmann constant. Why is it not writing? There we go. Sigma times the surface area and the temperature to the 4th power. And this is one of the few things in physics where we look at something to a 4th power, so to a large power. The reason for that is a complex way that these particles are interacting with the temperature. But I'll give you the Stefan Boltzmann constant is saying that 5.67 times 10 to the negative 8 watts. That's how much energy is being transmitted, because watts is joules per unit time, and so Q over T will be in watts per meter squared, Kelvin to the 4th. When you do radiation, this needs to be in Kelvin. Alright, so these are the 3 types of radiation, or 3 types of transfer of heat. Radiation and conduction are the ones we can calculate fairly easily. Convection, we use fluid flow to move the heat about. And so usually we do that as a fluid transfer, or we look at things like sweat and figure out how much energy is stored in the sweat. And we look at the specific heat of sweat and figure out that that much energy is going per gram of sweat. So we combine, convection really is a combination of all the things we've done before. In essence, radiation is the true transfer of heat in a vacuum. And this brings up a weird fact. Without any contact, objects will still radiate away heat. And since things move from a higher temperature to a lower temperature, right, T high to TL, the universe will lose heat. It will radiate it away into light. And eventually, all particles should stop moving. we're going to explore this idea more and more as we learn about how all this stuff comes together. We actually have a calculation for that. We're at about 10 trillion years until the universe is expanded enough that all the particles stop moving. And we'll look at it in a lot more detail in chapter 15 when we look at the laws of thermodynamics and the mathematics that ties all of these things we're seeing together.